Part 5 of Unit 11 is about Le Chateliers Principle. The definition of Le Chateliers Principle is that if a system at equilibrium is disturbed by a change in temperature, pressure, or the concentration of one of the components, the system will shift its equilibrium position as to counter-effect the effect of the disturbance. There's a picture of Chewbacca here because a former student couldn't spell Le Chateliers Principle and they wrote Chewbacca's Principle on a free response question, and I thought it was funny. It's been stuck with me ever since. The gist of Le Chateliers Principle is if a system that's at equilibrium is stressed, it will shift to relieve that stress. And there's a few general rules for us to remember when this is happening. So we're going to use this equation as an example. N2 plus 3H2 yields 2NH3 and everything's a gas. So if our stress was to add hydrogen gas, we're adding a reactant. This equilibrium is going to shift to the right. And that means we're going to make more products when we say it's shifted to the right. We increased the reactant concentration. It made more products to restore equilibrium. If our stress was adding ammonia, NH3, the shift is going to be to the left. There's going to be more of the product molecules made because the product concentration was increased, so some product broke up into reactants to restore equilibrium. If we removed nitrogen gas, we took away some of the N2. The reaction would shift to the left. It would make more nitrogen gas. The reactant concentration was decreased, so some of the product is going to break up into reactants to restore equilibrium. If we took out some of the ammonia, NH3, the product concentration was decreased, so it's going to shift to the right to restore that product concentration to restore equilibrium. So those are how affecting concentrations can cause equilibrium to shift. So those are examples of stresses being placed on a system at equilibrium and the system shifting, either making more reactants or more products to relieve the stress that we put on the system. Now let's pretend that this reaction is exothermic, and it's got a delta H of negative 92.2 kilojoules per mole. When a reaction is exothermic, we can add these kilojoules over here as a product. So we'll put plus 92.2 kilojoules. That's given off to the surroundings. The opposite's true for an endothermic reaction. If this was endothermic, we would put the plus 92.2 over here on the reactant side. So we can treat this heat as a term. So it could be a term to be stressed just like a reactant or product was. So the page before we said if we added NH3, it would shift to the left. If we added heat to this reaction, it would shift to the left. You just have to make sure you pay attention to what side of the reaction you put that heat term on. For exothermic reactions, it goes on the product side. For endothermic reactions, it goes on the reactant side. Another thing to remember, if pressure is increased or volume is decreased, the equilibrium will shift to the side of the reaction that has the fewest moles of gas. So it's going to shift to the fewest moles of gas. So if we increase the pressure of this reaction, it's going to shift to the right because there's 2 moles of gas over here and 4 on the reactant side. If we decrease the volume of the container, same thing, it's going to shift to the side with fewest moles of gas. Now the opposite of that is true. If pressure is decreased, or volume is increased, that is some ugly writing there, sorry about that, it's going to shift to the side with the most moles of gas. So if we decrease the pressure on this system, it's going to go to the left. There's going to be more products made, or more reactants made, because there's 4 moles of gas over here and only 2 on the product side. Just a quick note about catalysts. They increase the rate of both the forward and reverse reaction. They're not going to have any effect on the equilibrium or Le Chatelier's principle. It just means that we reach equilibrium faster, but it's not going to affect concentrations of any reactants or products or the equilibrium constant. It's just going to help us get there faster. Your question for this section: in which direction would the equilibrium shift in the above reaction if the volume of the reaction container were increased?